Start recording. Okay. Let me see. So we've been out for like 2 weeks. So let's do a bit of revision. Last time we were looking at basically this situation. We've got a shape coming in. Try and reuse the same colors. So it's got some velocity coming in to a surface. It's going to impact that surface at some point. And then we want it to come out with essentially that velocity reflected on that surface, you know, your standard bounce. So we also, you know, we know the normal to this surface, which we get from the separation. So you'll recall that when we separate, it tells us the minimum axis of minimum separating axis, which will of course be this distance here, which we can use as a normal up here. And there may be some I guess numeric issues we want to consider when we do this as well. And then we took
No, I'm just trying. I know that by the end, I know that was a pretty grueling one for me, and I remember at the end of it, I sort of like dictated back the specific process that we went through, to achieve that. Now I can't remember it.
That's all right. So I'll reconstruct that diagram. We'll just do it as a revision, seeing as we've done it already. So basically, we took this diagram, which is like, I forget what I call it, but it's like the sort of in context, I think, diagram. It's like this is sort of a representation of what we want the world to look like, I guess. Anyway, and then we take all of these vectors. So we've got 4 vectors, and we plot them out just as vectors in, you know, some just context-free space. So we've got like the tangent to the plane. We've got the normal. And these are normalized vectors, so you can kind of think of them as having like being an axis in and of themselves. So just like we have the x and the y axis, we've got these n and t axes basically. And then if we draw the velocity vector we started with onto this system as like basically that, and then we want to do a reflection. So do you remember how we did this reflection?
I remember we sort of, like took the perpendicular, like from the red arrow down to the green, or sorry, to the magenta axis. We kind of project that down, like that, and then the other one.
Yep.
Yep.
And so that gives us sort of 2 projections. So we project red onto magenta and red onto blue, and it gives us that and that if we did the vector projection. But we can just use the scalar projection and get the distance and do the multiplication, I guess. And then all we did is, you know, we're going slightly orangier. Or how about grayish pink? So we're going in to the thing here, but rather than in, we want to go out. And so we basically did that. We flipped on the normal axis. So we take all of this here, but we take the negative of this one here, so we come up there, and then we can just do a bit of addition to add those 2 things together, and then we get the final result, which will be that. So probably a little bit straighter, but you get the idea. So does that all seem familiar and make sense?
I mean, I don't have a firm grasp on it, but it kind of looks like the green arrow. Like, is it just drawing? Like the green arrow looks a little bit too close to the sort of x-axis. Is it just
It's just
drawing?
poor drawing, I think.
Okay, yeah, no worries.
So you can sort of see because it's kind of like rotation. I don't want to really call it a rotation, but you can see it's red is pretty close to y, so
right.
Green being close to x is not unusual.
And there was last time there was sort of you kind of had to lead me through it by we did the mirroring, the obvious mirroring on an axis aligned example.
Oh, yeah.
And then that sort of led us to, well, we just, without the concept of axis alignment, we could do the same thing. And then you kind of brought it into context-free space in order to show that the math was pretty much, well, it was exactly the same. And then we just applied that back. I'll have to review the last video to get that sort of, I kind of laid it out to myself in like a specific set of steps that I think will be useful to review later.
So, just to...
Because I saw what you did there, but you kind of just did it intuitively last time. We sort of said, once we got to the red arrow, it's like we did perpendicular projection onto the t hat and n hat axes, and then how you got the green arrow was right now is sort of just like you mirrored the n hat. Well, you mirrored the red vector right across the n axis. It's just hard, yeah.
So, and then what we have is if this is what do we call it? The V, and let's call this V1. So V1 equals A. So we have all of A minus B, which is this one. So it's, or if you like, it's A plus negative B. So this is how we get V1. And these are all vectors. And so what we can do is we can sort of break this down if we the way we'll probably implement it will be more like V1. And I think just for reference, I've actually swapped A and B from last session's diagram, but that's slightly nicer anyway. So we've got A as a scalar times t hat plus, minus or plus negative B times n hat. So this is going to be the formula we'll actually use. So rather than, is basically, A as a vector equals A times t hat. It's just the sort of formula that we're using. But yeah, so this is going to be what we'll program. So are you comfortable enough with what's going on here to head over to the code and start doing some things with this?
Well, why not? Let me give it a shot. I'm not 100%. I can't exactly remember where our normals are in this example, but
okay. So one last thing I'm going to mention, and that is how we actually get A and B. So now I have to think about this. We have to do the scalar product. So if we do A, for example, A equals V dot product T hat. Does that make sense? So you recall from our projection stuff. So I just draw that on its own.
Oh yeah, sorry. V is red. Put in the context of T.
And so our projection is basically we're projecting onto this axis here, at 90 degrees. So we end up with the scalar A.
Dot product's what's giving you the projection there?
Yes.
Why am I getting them confused with perp?
Perpendicular would be how we get from n to t is perp 90. So if we have n up here, n hat, and then we want t,
right,
90 degree angle there. So that's
that's
perp.
Okay.
This is a dot product, but this whole operation is projection.
Right.
Right. And there's kind of different forms of this, like scalar projection, vector projection. And what I'm doing here is because I've got a normalized vector here, I can just do a straight up dot product. I don't need to do any normalization in there.
Right, because t hat is already a normal.
Yes. So, shall we
sure
bring this over into the code?
I was looking at where to do this, though. Simulation. Can't actually remember where we even were in this.
So we were talking about this. We were like, all right, we want to. That's right. We have S to do calculate separation, but we left this comment here and now change velocity. So rather than doing this on the S key, we kind of want to do this just all the time. So we can just grab this block of code and stick it over in the simulation. So why don't we grab that and copy it down. So we probably need to put this in a sensible place. After everything updates, I think is probably wise.
And actually have your comment.
So these three steps are like the basic steps. Move things, detect collisions, respond to collisions.
Right.
Okay, so we're pretty happy with detecting collisions, and now we just need to respond to them. So why don't we first, just to test that we move this correctly, we're just going to get rid of the S key entirely for now. Let's just run this and see if it works the way we expect it to. So if I make a box and another box, and am I paused? I'm paused.
What's the pause key again?
Enter. I know why I'm really stuttering because I'm running OBS. There we go. So you can see if they collide now, they will separate just continuously. You already got a little bit of physics action happening.
Having trouble here. I don't know what my keys. Oh, second mouse button for that. Okay.
So I've already got a bit of physics just by doing that. So that's not bad.
That's like auto. This is basically just auto separation because we're doing it in the simulation tick now.
Yeah, and so if we bring these two shapes together, however, if they can slide past each other, if they stop colliding, they maintain their own velocity. So this is what we're doing, is we're now changing their velocity based on the collision that's occurred.
Right. Rather than right now, we're basically like the victim has got no velocity at all.
Yes.
Right. Okay. That makes
And
sense. Whee!
that's the other thing I wanted to just briefly mention, and that is we talked about elastic and inelastic collisions and that sort of thing.
Yeah.
So that's what we'll come to next. So for the time being, we've kind of just assumed that one shape is moving and this shape is fixed. So we'll worry about what happens if both shapes are movable and the way the momentum gets transferred and so on. We'll worry about that after we actually get this part working.
Right. Okay. Well, what do I have? I've got. I'm assuming I've got what we were calling.
Let me try and bring up this.
Yeah. So that I think this is V. This is obviously V.
Yep.
What's happened? And then, let me see. So if I want to get, I want to get T hat and N hat.
Mm-hmm.
I wonder how. Hold on. N hat and T hat can't actually. It's the, what is it? It's the blank to the normal. Is it perpendicular to the so like the normalized T is perpendicular to the, well, it's perpendicular to the normalized N. So
T is really easy because we just do the perp 90 on it. So N is what we really want.
right. Okay. Oh. Forget UI for this.
I think did we make an extension method? So I think you need vector N and then exactly. Although that
That's T, right?
Yeah. So,
and then for N.
So
N,
well,
need...
hold up. So T should be N dot perp 90. So you just need to add in N.
Oh.
Yeah. You got it.
Oh, yeah.
You got it.
Hold on. T is N perp 90, and N is.
So we'll come over here. This is This is the separation, and this is N. So we can derive.
N is the normal of the axis that we bounced off.
Yes.
And we should know that. Hold on here. We have to surface this out of the calc, don't we? I'm just gonna look at this. Hold on, axes. Where are we getting? Axes is stack alect, and then axis, and then separation axis. We don't actually tell us what the separation axis was.
Okay, so I'm gonna jump ahead because I was gonna do this as like a second step, but I'm gonna jump ahead and let's talk about what is happening here. So I'm gonna bring this back over and we'll have a quick.
I figured we were gonna just change the API to like out the separated axis.
Well, now that you've mentioned it, I think we will do exactly that, because let me describe why. So what's happening is we're getting two shapes colliding, and we've got some overlap, and we discovered that the axis of separation is basically the normal to this one here. So we've got that. So that's separating axis, and then we do the calculation that tells us, this is the distance to separate. And then we do a little bit of division, so it's like the triangle gets like half of it, and the circle gets like the other half of it, depending on their mass. So we're doing a mass calculation there. And that's an okay start. So we could just take this one here and just be like, all right, it's that, and we'll just normalize that. So it's, length of 1. So we could just do that. And that was what I was kind of going to go for. But there's a whole lot of problems with that. First and foremost is this normalization operation, which we may still have to do. involves a square root. You'll recall that, in fact, if we look at
Yeah, I actually don't know how to do it the way you wanted to do it just now.
so v dot normalize is this. So you recall we got the length and we divide it by the length, and that's kind of an expensive operation given that we already start with the axis. So we could derive the normal from the separation amount, but there's a couple of problems with that. First of all, if they're barely touching, and you recall we were having some numeric problems because they were barely touching, we already have this axis as like correctly lengths and normalized and everything. And then if we multiply it by like almost 0, we're going to get like tiny, imperceptibly small vector. And so when we go to normalize it again, we will get some sort of error. We could end up with something coming out there just because of numerical problems. Do you sort of understand how that works?
Yeah, sort of.
So basically doing like, really, really tiny vector divided by really, really tiny length and hoping that this is going to be, 1. And, it might be. But if this is small enough, this could actually be a serious problem.
Yeah, but I don't actually know how you would have gone about deriving the, like, if we couldn't do what I wanted to do, which we will do, like if we're back here at n, you were saying that you could derive it from the separation amount itself?
Hang on. Yeah, so we can derive it from the pending separation. And the reason we can do that is if we look at calculate separation, we're basically just undoing this operation. We're taking, there's the separation axis, and we're just undoing the change of length.
Right.
So this is a vector with a size, and we're just getting rid of the size. So we're getting back to separation axis through a bit of maths.
Right.
So that's what normalization is.
It wouldn't. Well, yeah, but it wouldn't have occurred to me to try to do it that way. I figured it would just be in here. But yeah. It's a failure. But
the other thing that I wanted to point out is that if we've got two shapes doing like doing this, in fact doing something like, say, this, then we're going to have two separation amounts that are like that and like that. And so depending on, you end up in a situation where if you're coming in here, it depends sort of how fast this is going, like where the frame boundaries are as to how far it goes into each of these. So you end up with like on one, if you land in this same sort of position, you could end up with a result that looks like this, and then you normalize it out to like there, even though what you really want is something that looks like just the surface normals, so like that and that. And what's going to happen is you add those up there and pink there, and you end up with something that's coming straight out of those two things. So you kind of only want to take into account the actual normals and not the separation amount, which is, that's fine that you didn't even think to do this, because I guess this is not actually what you want. But do you understand sort of the difference there?
Yeah, although this brings up another question for me, is like I don't think, like we're not doing like we're doing this in order, like shape. So would we ever actually overlap two shapes? Like wouldn't have this triggered on, wouldn't we have calculated the separation? Like I guess if it was moving, like I don't think we'd ever see this. I guess this is more like if we did it in the editor and like made it overlap by creating the object when it was paused and then unpausing it.
Well, you can imagine that this shape might be moving so fast that on the previous frame it was like out here. So it moves
Oh, that
like
is true.
that
Yeah.
far on one frame.
I was just wondering if that's the only situation that could occur because of the fact that like we don't do, I guess, I don't know if it's called like a two-phase update or something where you would kind of you kind of traverse the list twice and look for both as opposed to like
Well, we are
just
kind
doing
of
them one at a time.
we are kind of doing that. Like we're getting all of the
Right.
separations, and
That's
then
right.
the only thing we're getting out here is the addition of the two things. So the green arrow here is what this shape sees. It never sees blue or pink, just green, because we've already done the n squared step, and now we're in an n loop. So if I bring up this, you can see here's the n squared part where we're doing each shape for each shape, and then the result we're spitting out is just n, and so we have this for each shape, and we're just doing the output data.
Right.
Okay.
Yeah, I think I'm confusing it a little bit with the sort of general problem which we had in River City too, which was just that you have a bias if you have like actors in a list, and you have a bias if you do the update on the first one versus the second one, especially if you're trying to resolve two collisions at the same time. Like two players punch each other at the same time and they both hit. Well, you're always gonna give that win to the one who got in first in the update list, kind of thing. But
Exactly.
I can see how that's not really the case here.
So
you kind of already account for that.
Exactly, and in fact, on River City, well, because of the fight logic was obviously so complicated, I think in hindsight, if we were maybe redoing it, we might have done the fight logic in a two-phase thing where it's like, all right, gather all the collisions and then spit them out. I guess that then you might be in the odd position where you, on the same frame, two players could hit each other on the same frame, and you have to have perhaps some way to deal with that. It's never going to be the case that like both players fly backwards from a hit at the same time, and maybe that's what you want for gameplay or what you don't want. But the physics for River City was two-phase, so it was all like frame, or it was order independent.
Right. I mean, I think there would be cases where you probably would want both people to connect with a hit and both be damaged by it. But yeah, that's it. Yeah, I mean, that's actually kind of a controversial topic in fighting games. I think about where some games they have that players can kind of intuit what advantage they have because they don't do that.
Exactly, and yeah, you can imagine that if you did put in the option of like both players hitting each other at once, maybe you'd want like new artwork and stuff of that too. So like
that's very true.
It's a question that like sort of needs to be answered deliberately, and
Otherwise, both players would fly back, and you wouldn't even see the connecting punch of either one, so it would look ridiculous. Exactly. Both of them would wind up, and then they'd both go but you wouldn't have actually seen the effect of it. So
exactly. Yeah. Although yeah, and so then you have to consider frame timing a lot more carefully, and obviously we didn't really have time for that.
Right. But I guess you could also tell the engine like play through it like your what you would have hit with just to see it and then go into your victim.
That's how I would have handled it. Would be like hits get stored up. It's like a hit registers on a frame and the animation plays. Like I guess what I would probably approach it as is still a two-phase thing, but instead of doing phase 1 and phase 2, like register and phase 1 being register hit and phase 2 being respond to the hit, rather than doing them on the same frame calculation, I might delay them by like 3 frames. So all of the hits, like they register on frame 0, and then the result plays like a couple of frames later. So you get that game feel thing where you actually see what happened.
Oh yeah, I like that a lot. Yeah, that's what you mean by frame timing. Yeah, okay. Yeah, that's probably very reasonable.
So this approach is quite good. Like doing things in multiple phases. It just means that you have to keep some memory around to store the results. So
Right.
the last thing I'll say here is, and this is sort of a subtle point. So as I was saying here, we want length 1
Right.
here because we're using that as an axis over for our projection calculation. And so if we were to add these up, these have arbitrary lengths, these ones. So we have to do a normalized step. But also, if we're adding 1, 2 normalized vectors together, this is going to be not length 1. You're going to actually have to normalize this one as well to be
Right. Yeah.
length 1. So, but if there's only one of these, like if it's just that on its own from, I don't know, a shape that looks like that, you can just ignore the normalization step, which maybe we want to do because that's the common case. So we could optimize that fairly. We could make a guess at the best way to optimize that and stick an if statement in there. So that's where we're going with it. You happy with all of that?
Yeah, I mean, I'm gonna have to remember that down here because I know we're only like looking at the greater than 0. We're not looking at like 1 and 2 and so on. So I'll have to think about that harder. But
exactly,
I can start.
Let's make a start. So yeah.
Yeah, I mean, I think I'm gonna want well, I'm just gonna want a bag of axes in my method. So I think I want to pass in an array of axes that I will fill. A bad name because we already. Oh, it's right there. Okay, so I just want to pass that, I guess.
Now,
Okay.
Before you do that, just note that axes has a specific meaning within this method. So inside this method, axes is actually, I'll draw this in red. Axes will be that axis and that axis and that axis and.
Oh yeah. Okay, I'll call them separation axes then.
Yeah.
That seems more like. Yeah, you're right.
Yeah.
Whereas these are all like that's just the candidates, not the winners.
Exactly.
Okay. We'll make one of these. And so yeah, okay, hold on here. I guess this will be. We don't. I mean, what's the size of this is only going to be this if that intersects. So I might have to keep an index or a counter around. I'm just trying to think of this.
So well, if it does intersect, we already have that. So we have this guy.
No, I know, but I'm just thinking. I don't know. Like, I've got this, and then, like, okay, look, I know that I, intersected here or here, and I want to put this is I guess the thing. This will be on a different count than, it won't be K because not all of these will hit. That's what I mean by keeping a counter. Like I have to know. I'm just trying to.
So I just want to draw something out for you just to clarify what's going on there. So that code you're looking at is, say we have a square and there's a circle hitting it like that. So one axis is going to be, hey, you collided on like this amount here, and the other one is going to be you collided on like this amount here. And so the thing we're doing there is we're selecting the minimum separating. So we actually want to ignore that one and just use this blue one here.
Yeah, you're right. Yeah, so I only need to add it down here, basically.
Exactly.
But again, I still don't know what. Oh, I do. It's intersection count. Derp. Wait, why are there 2 here? Did I do that, or is that just the way it is? Oh, I and J. Yeah.
So yeah, these are the two shapes that have collided.
Yeah. Yeah, this is I don't actually know. Well, there's two, so yes, I can do this. Or wait. Well, no. Oh, I don't think this is right. What am I trying to? I need the number of intersections. So I guess that could just no intersection count. This counts per shape.
Yeah.
So
So what we've got here is we've got one of the, like the blue or the pink one, for example.
the pink one.
And then
Yeah.
and then we have, so that might be I, and then we have the opposite. So we have for the circle we'll have basically that, and yeah, like that. So just to clarify, like I might be the light blue and J might be the dark blue, and then we'll come around for another set of shapes. So that's testing this circle and this triangle, and then we'll come around for this circle and this triangle, and we'll have I might be the pink one and J might be the dark pink one.
Yeah, I know, but I'm struggling because obviously there's only one separation axis per go around, so I just don't. I'm just not confident in this being right.
Okay. Well, let's look carefully at the code we already have, and look at how separation axis is derived, because we know that basically separation axis is right, like loosely speaking.
Right.
So say we have a blank space to draw on. Say we have this shape here and this shape here, and we come out and we're like, okay, they did intersect, and we have the separating axis, and it is something that loosely follows that line and is, a unit length normalized.
That's right.
And so it's just a question of, right, we're then going to want to output it for both of these shapes. So the circle might be the circle, we kind of want it to be that, and for the triangle we actually want it to be that, because we're getting the surface normal. So when we consider them on their own, we've got the triangle and it's doing that, and we've got the circle.
I guess my hang up is
doing that. Yep.
Thinking that the separation axes array has to be compact. Whereas like if we're using I, and like we're gonna get one of those for every shape, but there'll be cases where it doesn't intersect, and therefore that memory location in the separating axes vector will be not assigned.
Yep.
And that's when my problem is with this, is that this isn't like what I would probably actually want is this before I add to it.
Okay. Yeah.
So I can go 0, 1, you know what I mean? Like if I did that, then this would only represent the axes, but maybe what you're saying is that that's not actually useful to compact the vector.
Well, what you're talking about is, all right, there might be, for any given shape, so let's say this circle here, there might be 0 intersections. It could be like a circle just sitting on its own.
That's right.
There might be 1 intersection, in which case you just have one separating axis. But there could also be the case that there may actually be 2 intersections, which is the case with this circle, or more.
Right.
And so we have to handle all of these cases. And so what I want to draw your attention to is I've already drawn sort of how we might handle the 2 case, and that is we've got the blue and the pink over here, and we've just added them together to get what we want the result to be, because we're going to handle this in a single pass, so we can't consider each collision individually. So effectively, what the circle is seeing at that point is it's seeing this is its surface normal. So it kind of, from the circle's perspective, it's just hitting a flat surface with this normal because basically it hit both of these things at the same time.
Yeah.
So
Yeah.
and the way it gets handled is going to be very similar to the separation, basically. So it's almost literally the code up here. So you scrolled.
Yeah, I'm kind of lost. I was thinking like I have to basically just, if I was gonna check the intersection count and then like, add them. No, I don't. Yeah, I don't really know where I'm gonna. Like, I can see what you're saying, but I don't know how to get there from here.
Okay, so I'm just going to stop you.
This is separation A, right?
So I'm just going to stop you because what you've copied out is data that we're not like we don't have separation A, range A, and all of this data is inside this loop, and so it's not going to make sense to pull that out because we're selecting like the best one. So we've actually lost all this information at that point, which is fine.
Right.
Because all we want is the separation amount and the separation axis. We will have to consider directionality in a moment. But for the time being, let me just write some code for you just to give you an idea of what we might do. So basically, the idea is that and that.
Oh. Yeah, well, that makes sense. There. Right. That's you continuously adding to any possible. Yeah, that makes perfect sense.
Okay, and so you can see how if this is the zero case, this is never going to hit. So this is just going to be zero. But up in our loop over here, we're gonna wherever our loop is, we're just going to be like intersection count is 0, so we just skip over that shape.
Yep.
If it's 1, we can do the thing. If it's 2, we're going to have to do this normalize. Don't know why we have v.normalize there. Oh no, that was just me scribbling.
That was just you, yeah. And it's and it's totally. Yeah. Okay.
Yeah, so if it's 2 or more, we'll have to do.
Stupid now, but I get it.
No, I
totally
mean,
get it.
That's just a leap, so that's fine. But the thing is, and this may be what you were getting stuck on, is you can see that
normalize still.
Well, we have to normalize once we're out of this method, but in here you can see we're flipping the axis because we've taken the convention that it's always pointing towards shape. It's always pointing towards one of the shapes, and I think it's shape B.
Right, but in our case, that's going to be doing the wrong reflection, isn't it?
So I suspect, and I think this is why we've made this convention, is what we actually want to do is something like this. And I'm just trying to work out which one is which. Do you see why, however, we need to do that?
I don't know why why it's J specifically, but I do see that.
Yeah. So I have just realized that I actually don't know whether it's supposed to be that or the opposite. You see.
Yeah.
So let's try and figure that out.
But yeah, it makes sense because all of whichever one it is, those will all have been flipped around. So we need to flip them back by going the opposite direction.
Exactly. So let's have a quick read of this code.
A is less than B.
Oh, okay.
So yeah, A should always point to B. Because if it doesn't, if B is pointing to A, kind of literally, it'll flip it.
So A is always pointing to B.
Mm.
And we know that shape A is basically I.
Yeah.
So A is pointing to B. If that's the case, and I'm going to trust you on this one. So if it's wrong, we can just flip it back the other way.
Right. But yeah, I think it's plus. I think it's plus and minus.
I think, yeah, and so it should be plus and minus.
Right. Well, 50-50. Anyway, but I think I think a reading of it says that. Okay.
So let's give that a go. And if it's wrong, I mean, as you said, it's 50-50. And this is the sort of thing that's like, I could think about it, or it's 50-50. And like, I understand what the difference is. So we can always just try the opposite and be like, oh, yeah.
Right.
Because
so
we understand what the theory is.
Right.
That's fine. So let's finish
I
up
gotta,
here.
I gotta do some clean up stuff here. Operation axes equals stack alloc vector 2 shape count. And I guess I gotta do this part too for funsies.
Yep. So
Roll 2-0 and pass that in here. And I think I got to do the same thing in the draw world.
yes. Now, I mean, we may as well just stack allocate and just call it a day. I mean, there's nothing.
Oh, is there a different?
Like what we could do, we could pass null in and detect null. It's like, oh, we don't need this information, so we're not going to set it and stuff. But
right.
For the sake of today, we'll just copy and paste it.
Okay.
The draw code is just debugging anyway, so
right.
No big deal.
Okay, so last thing is I think we need more than this, greater than 0, because we need to. In the case that it's 1, we don't have to normalize. In the case that there's more than 1, we do because we performed an an addition of vectors.
Yes.
But yeah, so so if I don't like this 2 if thing, but I'll worry about that in a second. If it's greater than 1, then separation axis I normalize. Oh wait, is this that? This is a value type, so no, it's void. Okay, it mutates. All right, and then
I might actually make a point here, and that's the API is not very good. But if you want to return, and which we probably do,
yeah, I kind of feel like I wanted to.
You can use vector2 dot normalize.
Oh, the static one?
Yeah,
it's true. Okay.
Which is typically what I reach for, but it's almost a matter of taste.
And then I want to know n is just separation axis I, and then t is the perp 90 of n, and then a is gonna be v dot product.
So yeah, vector2 dot dot
e 2 dot dot. The first one is v, and the second one is t. Ref t. Ref both of them. It's a weird thing. Wait, I don't think I'm doing
big difference.
Hold on a second. I don't think I got that right. No, I didn't. Okay, back. Yeah, just bt. So that's a. Now, why do I have a? A was, yeah, a minus b is gonna give us v1. What's b? B is what is b?
So this is the diagram you want to be looking at. And it's like B is
n, or sorry, it's b is n dot t, or b is
yes, it's n dot t or t dot no, not n dot t.
v dot n.
Yeah.
Yeah, sorry. Sure. Okay, and then the thing we wanted, which I guess is,
so we call it V1.
V0. I thought it was v prime. That's cool.
It was V prime last week.
Oh yeah, right. Okay, yeah. Subsuperscript versus subscript, but yeah, okay, got it.
I realized
So
if I call
V1
it,
is,
yeah, it looks like a derivative if I use prime. So there's a minor issue here, and that is A and B are scalars. So they're actually this one here and this one here.
oh,
So you're going to need to do the multiply after you do the thing. So we're going from a scalar projection to a vector projection. So I'll just bring up the Wikipedia pages on both of those because they're. So here's a scalar projection and here's a vector projection. So it's the same concept. Vector projection gets us the vector A1 from A if we're projecting onto B, whereas this just gives us the length of A1, and then you have to multiply it through. Let me just verify I have, yeah, okay, so vector projection, checking I got my maths right. I'm going to say yes. So that looks pretty good to me.
all right. So when we say change velocity, I assume we actually just mean Jake's I velocity plus equals v1.
Not quite. We're reflecting, so we're actually going to set it to v1.
Oh. I always think about it as like applying forces, and I almost never set the velocity, but that makes sense. Yeah. Okay.
So in fact, we don't even need v1 at that point. We can just be like, all right, shape velocity equals that. This looks pretty good to me. I'm going to make one minor adjustment, and that is I'm going to suggest we move this one down in here, and rather than setting it back into the memory location that we have, we're just going to do it on the stack just for performance reasons. It's like, okay, we're telling the compiler we don't need to modify that array. And it's sort of speculative, but it's just sort of we're hoping that this is slightly faster, basically.
Right. And there's no advantage to there's no problem with this nesting, right? This like double check.
No. So we know at this point we know it's greater than 0, so we have to do something. And at this point we know it's greater than 1. So what's going to happen as far as performance goes? Well, this is going to get branch predicted as not being taken. Because this is going to be very rare. Most of the time our shapes will be flying through open space. So this is almost never going to fire anyway. But even if this was firing constantly for some reason, it's likely that this is never going to fire because we're only intersecting with one shape. So this will also get branch predicted as not taken, and so it'll just get skipped over. And then what will happen is it will skip over and queue up actually doing this calculation here. This is the intersection count greater than 1, and it'll say no, it's not, and so it'll say, well, that's fine. So you get this takes, if it gets branch predicted correctly, this doesn't happen effectively,
right?
And because this is an integer calculation, this floating point, I guess, yeah, it will take up a small, it'll take up some instruction spaces, maybe, but not much. So it's not a big deal.
Maybe to settle a superstition at the IL level, like when I know that so technically a managed array, like well, I guess this isn't managed, is it?
No,
No, it's not.
well, yeah. So
Um,
that's just straight up.
right. So this just refers to a location in memory, right?
Exactly.
I just want to confirm that and I'm pretty sure this is true, but there's no whoops, hello. There's no advantage to this, right?
Um,
I think there is with reference types because you're technically passing into the class like you're going into a reference type to do an array accessor, which is a culvert, right? But in this case, it's unmanaged, so it doesn't have any value. I'm just
no.
curious.
I don't think what you said particularly made sense. So, but what I will tell you is there are cases you want to think about that. So, the reason you see this a lot is because if you're not a managed, not a unmanaged array, which is a stack alloc, and not a managed array, which is like this guy here, but
Right.
a list. So list vector 2. You recall
No.
that you can't do this. You can't modify the member of the list because this returns by value
Yeah.
rather than by reference. So you can't make a modification to the result and expect it to get stored back into the list, which is a
That makes sense.
little
Yeah.
bit
That
confusing because the notation is exactly the same, but one works and one doesn't.
right. I'm familiar with that. I'm
Yep.
more interested in. I guess you
Okay.
said what I
Yes.
said didn't make sense. The class or sorry, managed versus unmanaged array access.
Okay.
You're saying
Let me break that down for you too. So what you said is something about performance,
right.
and that is there a performance advantage to doing this here? And
Yeah.
the answer is, I'm just trying to think exactly how to put it. And like this is something that I kind of don't pay too much attention to because it's not a huge deal, and often compilers are fairly good about this. But
Yeah, I figured they would have done it for you, kind of thing.
it is the case that if you pull something into local scope, you are telling the compiler, okay, I'm not going to be re-accessing this from memory, so you can stop tracking it.
Yeah, and I guess like I've instinctively done it that way for as long as I can remember, um, to avoid like um, always using the. I'm looking for the accessor here, but I can't find it. Um, anyway, I've just always done that out of, I guess, almost habit, and because I believe that it would be more performant. But I was just someday I'll have to get into IL Spy and see if basically it does it for you, and there's no point in because it's
I
more
don't think.
readable to keep out like this, like versus always having to have some storage for
Yeah.
something
And
like that.
that's the primary concern is you do the more readable thing, and you only do something else if you actually care. But you can imagine if this was say multi-threaded code.
Yeah, you'd have to do that to bring it into scope because otherwise, yeah, you'd be.
Yeah, and I can't remember any of the rules off the top of my head right now. But you can imagine you might actually want to read it twice.
Yeah, especially if you have if you're on an iterator or a lazily evaluated collection as well.
Yeah, and so that's not only something you have to take care of for multi-threaded correctness, but there is like you do need a way to tell the compiler it's like, okay, I want to read this twice. So you kind of need the opposite. It's like, all right, I want you to read this once. But
Right.
for yeah, so it could, and it could be the case. It's like, all right, compiler, I really want you to put this into a register rather than reading it out of memory both times. But what the compiler does there is something you actually need to look at the CPU for. There is I saved this away for for maybe later, but and I don't want to get into too much detail on it.
Yeah,
But
derail.
let me bring this over
Uh,
because sorry, I missed what you just said.
Oh, I didn't mean to derail here. I just said this kind of comes up a lot,
That's fine.
just in general.
This is interesting. So I'm going to bring it along over here. This is something called sharplab.io. There's actually a great tool. Let me also bring that up. So this is what I use when I'm doing native code, and let's see if it does something sensible. So this is the sharplab one. This is okay. So this is the compiler explorer. So this is C code or C++ code, and it's telling us, I've got this function that's, takes a integer and squares it and returns it. So it's like, all right, it pushes RBP, moves RBP to RSP. So this is just doing some stack manipulation to handle the argument coming in. And then it puts that into EAX. So EAX is a CPU register, and it multiplies it again into EAX. So this is the multipliers happening there. And then it pops whatever RVP is, I can't remember off the top of my head, and returns. So this is the exact CPU instructions that this function does. So let me copy this into sharplab. Let's say we have a class C, and we have a method here. So it can decompile the C sharp code, but we can also decompile the IL. So we end up with blah 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 blah. We've got a here's a method and all of the garbage for the method. Or we've got a constructor for some reason. That's fine. Hang on, actually, maybe make this make a bit more sense and make it static. Okay, so here we go. Can I get rid of it? I want to get rid of that constructor. There we go. So this is debug. Let's put it into release. So it loads argument 0 twice onto the stack, and then does multiply, which multiplies the top two elements of the stack, and then returns basically what's on the stack, which is the result of the multiplier. Does that make sense, roughly?
Yeah, this is really great. I love this. This is a lot more convenient than poking around on a disassembler like it's all there.
Yeah, like ILSpy is great for bulk work, but for just checking like little quick things like this is not bad. Now this part doesn't work very well, I have found. It doesn't give quite the same things. But for a simple method like that, so you can in fact see that this, and I don't know why, I guess who's compiling this? I don't know. I'm probably not. Can I get a plus O? Is it O3 or 2? I can't remember the optimizer. You have to specify arguments to get optimized code, so this is probably just debug code. But you can see that this one here is just taking it from a register and taking it from ECX, putting it in EAX, multiplying EAX by ECX, and returning it. So obviously ECX is the register that the argument's coming in, and EAX is the register that the result is being returned in.
Cool.
And so yeah, you can actually see what's happening, and so you can start doing more complicated things like that. I don't want to get into too much detail here, but so you can actually see.
This is a really cool thing to play with, though. I can answer all my own.
Absolutely. So you can look at exactly what's happening on the JIT. So this gives you a rough idea, but maybe they've fixed it. But last time I tried it, this was not optimized. It looks like maybe it. I don't know. It's hard to tell from something so simple. But the code didn't match what the optimizing compiler did. Like if I if I run this in if I run this in release mode with the debug CLR turned off and hit view disassembly, I actually get different results. But it's certainly worth being able to look at these things. So I'll give you the link to sharplab.io in Slack just so you've got it on hand. So bring it. Cool. And yeah, play with that because it's kind of fun. Anyway, so let's actually try our code that we've just written. and see if we can bang shapes into other shapes. Does it reflect off correctly is the question.
No, I don't think so. Just based on the fact that the response is dead.
Make sure you're unpaused. So and we sort of push that into the thing, and you know what? It seems to be working. It seems to be doing exactly what we want it to do.
Really?
Yeah. Does yours not work properly?
I mean, I feel like it does. I guess it's just a game play expectation thing. I'm expecting the thing I collide into to move a lot, like to kind of move itself a lot further than it is now.
Okay, so this is what we're going to get into next time. So you recall we had. Let me see if I can bring up Wikipedia on this. So you recall we talked about this thing, elastic collision, last time, as well as inelastic collision, and we have all these formulas that we're going to look at next time, and you see what happens in this image here. This one's coming along and hits that one, whereas if they're different masses, it comes along and boom, and like they bounce differently and the velocities change appropriately. Right. So it's transferring momentum across. Sorry, yes.
Yeah, no, that's what I was just gonna say. We're not doing elastic collision because we're not transferring any force to the other object.
Exactly. So we're assuming that this object is fixed in place, and if we were doing so, like in a more serious way, what we would do is we would set the mass such that when we did this calculation here. So this thing here, if we say, okay, say J is fixed, it's basically that B move equals 0 and A move equals 1, such that the one that we're treating as fixed never moves at all. Does that make sense?
Right.
Yeah.
Yeah, because right now it does have a little bit of movement. I don't know how I got this one to move. Because I moved it.
Yeah. So the little bit of movement is the separation rather than velocity. So we'll add velocity in for the response later.
Cool.
But we actually are going to have to think about what these things are colliding with. So we actually will have to do a little bit more work, because up until this point we've managed to avoid tracking the n squared problem of what's colliding with what. But you can see that if we start to try and transfer a momentum, we're going to have to actually track individual collisions. So it actually becomes a bit more of a tricky problem. So we're going to look at that next time. So I had this grand plan of, all right, and then we do momentum transfer. It's like, hang on a second, we've actually got one more step to do, and that is we actually have to track collisions individually to actually make the maths work. But that's fine. In fact, we may shortcut it just for the sake of doing that, so that we can get that momentum transfer maths done without having to do the fancy coding for the collision tracking, because we've avoided up till now. So we'll go with that plan, and then we'll come back and start talking about how a physics engine might track multiple contacts at the same time, because that's a bigger problem. I like this thing you've got going in here, the sort of bounded. That's kind of cool. I feel like I need to recreate that in mine so I can see it at full frame rate, because that's. Oops. How did this go? We got like a whole lot of my unpaused. Right, and then if I make one in the middle and bounce it around. Yeah, that's kind of cool. That's very cool.
Yeah, because there's no transfer, those objects are like infinitely kinetic, so they'll never stop.
Exactly. And so you can imagine, like, if we set this up, we could maybe have a hotkey that changed these shapes from moving to static, which that's probably an interesting thing to do as well. So we'll look into that. Okay, let's wrap it up. Um,
Sounds good.
all right. Thanks for watching, everyone.